This piece of paper has two creases. I can fold each one individually, but folding both at once is physically impossible. Now this case is pretty obvious, but this is a big problem for complex origami. And it turns out that the solution will involve tacos, tortillas, and Facebook logic puzzles. It's day 6 of learning the math of origami from kindergarten to PhD level, and today we're looking at layer ordering. Here's a simple crease pattern. Folding it up reveals two stacks, one with 2 faces and one with 4. For each stack, we want to find an order of the faces that will not result in a self-intersection. This problem is actually similar to those logic puzzles you'd see on Facebook. These are examples of what's called Boolean satisfiability, or SAT, problems, where we assign things to true or false to make all the statements true. SAT problems are well studied, and we mostly know how to solve them. So now we just need to rephrase our ordering problem into SAT. So for any 2 faces in a stack, let's define a variable xij that is true if face I is above face j. Now we can write statements about these x variables such that the paper is physically satisfied. The first way our layers could intersect is called tortilla-tortilla. A tortilla is a pair of faces that connect across neighbor stacks. This example has 2 of them. Tortilla-tortilla intersection happens when half of a tortilla is above the other and the other half is below. We prevent this by stating that the order needs to be the same in both stacks. The second way is called taco tortilla. A taco is a pair of faces that connect within the same stack. Taco tortilla intersection happens when half the tortilla ends up inside the taco. We prevent this by stating that both sides of the taco need to be on the same side of the tortilla. The third is called taco-taco, between 2 identical tacos in a stack. Taco-taco intersection happens when only half of a taco ends up inside the other. We can prevent intersection by saying that of the 4 cross-taco variables, an even number must be on top. Finally, we also have transitivity, which applies to any 3 faces in a stack. If A is above B and B is above C, then we better have A above C as well. We can express this as a not all equal clause. So in total, this example ends up with 6 faces, 7 variables, 1 tortilla-tortilla, 2 taco tortillas, 1 taco-taco, and 4 transitivities. We also get a few extra constraints if we know the directions of the creases. Now if we just convert to conjunctive normal form and throw it into a SAT solver, we'll either get a valid layer ordering or find out that it's physically impossible. Now obviously there's a lot more math behind this problem that I'm skipping, but for now, that's why origamists love tacos and tortillas.